When an application transmits a live video stream, it can afford to drop data. A few lost frames manifest as a momentary glitch, but the stream continues. If you are downloading an executable file or processing a database backup, that same data loss is fatal. The internet infrastructure routing this traffic operates at layer 3 of the OSI model using the Internet Protocol, or IP. IP routing provides best effort delivery. It pushes raw packets from router to router, meaning those packets will inevitably arrive out of order, duplicate themselves, or simply disappear in transit. Core internet services cannot function on a best effort basis. Loading a web page requires fetching hundreds of distinct objects. Sending an email requires precise command sequences. A single missing bit will crash a mail transfer agent or render an entire file transfer unusable. To force reliability onto this unstable medium, networks rely on the Transmission Control Protocol, or TCP. Operating at layer 4, TCP acts as the critical intermediary between low-level network routing and high-level application requirements. By deconstructing the 20-byte TCP header that encapsulates application data, we can see exactly how this protocol enforces state consensus, governs flow control, and executes congestion algorithms to guarantee delivery. TCP's mechanism mathematically mandates a reliable, full-duplex byte stream between two hosts that share no physical circuit. Because TCP is strictly connection-oriented, no application layer data is permitted to transmit until a formal negotiation concludes. This negotiation is the three-way handshake. Step 1. The client initiates communication by sending a Synchronize, or SYN, segment. This segment contains an unpredictable initial sequence number, the ISN. Upon sending, the client transitions its internal tracking into the SYN sent state. Step 2. A server actively listening on an open port receives the request and replies with a SYN-ACK segment. This contains the server's own generated ISN, alongside a cumulative acknowledgement value that mathematically increments the client's ISN. The server transitions to SYN received. Step 3. The client returns a final ACK segment back to the server, verifying the server's ISN. Both hosts now lock into the established state. This precise variable exchange ensures that both endpoints have verified the other's capacity to receive and sequence data before transferring a single byte of resource-heavy application data. The handshake effectively establishes state, but its architecture contains a critical flaw. When a server receives that initial SYN packet, it must immediately allocate memory and queue space for a half-open connection while awaiting the final ACK. This requirement enables the SYN flood attack. A malicious actor targets a server with thousands of spoofed SYN packets, initiating the handshake but never returning the final acknowledgement. Because the server holds resources open for each attempt, the backlog queue quickly reaches maximum capacity. At this point, the server is forced to drop all subsequent connection attempts, locking out legitimate users. Network engineers mitigate this specific resource exhaustion tactic using a cryptographic defense known as SYN cookies. Instead of allocating memory immediately upon receiving an SYN, the server encodes the connection state directly into the mathematical generation of its ISN, the cookie, within the SYN response. This transforms the server's handshake process into a completely stateless operation. It allocates zero resources until the client returns a valid ACK containing the incremented cookie, proving its legitimacy. Once the connection is established and data transfer begins, TCP maintains order through cumulative acknowledgements. Every byte is numbered, and a single ACK verifies that all preceding data in the sequence has been successfully received. To prevent the sender from transmitting data faster than the receiving application can process it, TCP implements flow control. This is a strictly receiver-driven mechanism designed to prevent local buffer overflow. This animation visualizes how the receiver dictates this limit. In every acknowledgement segment, the receiver advertises its current available memory using the 16-bit window size field, or rwind. This value creates a sliding window, a hard limit on the amount of unacknowledged data the sender can have in flight, shifting forward only as the receiver consumes data. The original RFC 793 specification allocated exactly 16 bits for this field. Mathematically, this caps the maximum possible window size at 65,535 bytes. This chart shows the bandwidth delay product, or BDP. This formula, bandwidth times round-trip time divided by 8, determines exactly how much data must be in flight to fully utilize a network link. If we apply this to a 1.5 megabit per second satellite link with a 513 millisecond round-trip time, the link requires a window of approximately 96,187 bytes to maintain data saturation. Relying on the legacy 64 kilobyte window restricts this specific link to merely 68% operational efficiency. The sender is forced to stop transmitting and wait for an ACK because it hit the protocol's mathematical ceiling, not the physical network's limit. To solve this bottleneck on long, fat networks, modern implementations use window scaling. Negotiated during the initial handshake, window scaling introduces a bit shift scale factor to bypass the 16-bit cap. This alters the header's math, allowing for theoretical windows of up to 1 gigabyte, giving the protocol the elasticity required for high-capacity links. While flow control protects the receiver, congestion control protects the intermediary core network. The sender calculates a separate congestion window, or CWND, to prevent routers and switches from becoming overloaded. Legacy congestion algorithms like TCP cubic operate in phases. They begin with a slow start, exponentially doubling the transmission rate, before shifting into a linear congestion avoidance phase. This graph illustrates the classic sawtooth pattern of legacy loss phase systems. They have a fundamental limitation. They blindly push transmission rates higher and higher until a router queue overflows and physically drops a packet. They use failure as their primary signal to slow down. A modern alternative is Google's bottleneck bandwidth and round-trip time algorithm, or BBR. BBR abandons packet loss as a primary signal. Instead, it builds a dynamic model of the network path by actively measuring the maximum delivery rate and minimum round-trip time. Looking at this performance matrix comparing the two algorithms, the disparity on imperfect infrastructure is severe. On a link with just 1% packet loss, Cubic treats the physical interference as congestion and aggressively throttles its rate, collapsing to 25 megabits per second. BBR ignores the arbitrary loss and sustains 650 megabits per second. By actively pacing data to match the true bottleneck bandwidth rather than reacting to queue overflow, BBR mitigates buffer bloat and dominates performance on high-latency routes. When throughput degrades in production environments, network engineers use protocol analyzers like Wireshark to mathematically isolate the point of failure. Analyzing packet captures requires differentiating between error types. A standard retransmission occurs when an acknowledgement is completely missing, forcing the sender's timeout timer to expire. A fast retransmission operates differently. Triggered by the receipt of 3 duplicate ACKs, a fast retransmission is ironically a positive network indicator. It proves that while a specific segment was lost, the return path is still healthy enough to continuously carry signaling data. To locate the exact source of latency, analysts use the delta time heuristic, measuring the exact microsecond delay between two specific sequential packets. A high delta time measured between a client's initial SYN and the server's SYN-ACK proves a physical network-level issue. Because the server kernel handles this response automatically, the delay is strictly a product of geographic distance or a congested firewall. Conversely, if the handshake round-trip time is fast, but there is a massive delta between the client's HTTP request and the first byte of the server's response, the network is clear. The delay is definitively an application or database bottleneck. Mastering these packet-level metrics shifts network troubleshooting from guesswork to mathematically proven fault isolation. Terminating a TCP session requires the same precision as establishing one. Because the protocol is full-duplex, one side may finish sending data while the other still has information to transmit, requiring a multi-step graceful shutdown rather than an abrupt severing. This is the four-way handshake. The initiator sends a FIN segment, indicating it has no more data. The responder acknowledges this with an ACK. Once the responder completes its own transmission, it sends its own delayed FIN segment, which the initiator answers with a final ACK. Following this final acknowledgement, the initiating host enters the time-wait state. This protocol rule forces the connection to stay open locally for twice the maximum segment lifetime. This delay ensures that floating segments navigating the network's routing tables are completely drained before that specific port pair can be legally reused. Looking at this complete 32-bit TCP header grid, we can see how every field has a distinct mechanical purpose. The window size governs flow control. The sequence and acknowledgement numbers enforce order. The checksum verifies data integrity, and the control flags execute precise state management. Together, they independently resolve the chaotic nature of Layer 3 routing. From its standardization in RFC 793 to the updates of RFC 9293, TCP's state consensus remains the indispensable foundation of global digital communication.